Dear all, this exercise is called Tide and Salinity, and it aims to explore tidal movement and salt intrusion in a 3D schematized channel with the Delft 3D. So based on an earlier setup of a two-dimensional model, we will add tidal forcing and add a salinity boundary at the tidal forcing, and then we analyze the flow results with QuickPlot. This is the model that we generated before. You see clearly that there is a bend here and a rectangular channel. There's a blue boundary here, which we will make tidal. And there's a red boundary that is at the moment an inflow of fresh water. This is Delft 3D, and I loaded the two-dimensional model. If we go to the flow input, we open the file. It's called CO1. And we see the bend and the river, the domain, which is at the moment two-dimensional. And the way to make this three-dimensional is to add extra layers. So let's make a total of 8 extra layers. You get a message that will destroy the boundary data except water levels, because you indeed now need to have a three-dimensional boundary. I agree with that. And you see that because I have 8 layers, every layer has a depth of 12.5% of the total depth. These are sigma layers. So the size of the vertical layering does not depend, is not predefined, but is just a percentage of the total water depth. And in a water depth of 10 meters, this means that you have 1.25 meters. And in a water depth of 20 meters, it means that a single layer, vertical layer, is 2.5 meters. You can change the percentages per layer, especially if you have river flow. You would expect a boundary profile near the bed with sharp gradients of the velocity profile. You may decide to make a higher resolution at the lower layers. And similarly, if you have a lot of wind and wind shear stress, you may want to have higher resolution at the upper layers. For this exercise, I will keep it at 12.5%. There's not much more needed except for the boundaries that we have to revisit. First, I'm looking at the upstream boundary. That's over here. The upstream boundary is a current boundary, and we define it as uniform over the depth. We can also do it logarithmic. Maybe that's nice because that's more like reality. And if we look at the conditions, the flow conditions, we fill in here 0.8 meters per second. The default values that we just are overwriting are not very logical, so I don't know why they do that, but it's just to secure that you will look very closely at the boundary. The downstream condition, we don't change that at this moment. We'll just keep it as it is. No, we are not. I was mistaken. This is also a tidal exercise, so we'll make the water level being a tidal motion. So that means that this is river supply at the downstream, at the upstream side, and at the downstream we have a tidally varying water level. So we can predefine that in time series, but maybe better here to do it as a kind of astronomic or harmonic conditions. If we go for astronomic, we can edit the flow conditions, and here you can see that the M2 tidal cycle is automatically filled in by default. And of course you have then to change the amplitude, and you can add also the S2 component if that's important, but also components like K1, O1, etc. If you want to add more tidal constituents, you go to table and you say insert row above, and you can define more tidal constituents. Here there's end A and end B. That means the end of the boundary. The boundary has 2 points. It has a begin point and a start point, and you can also make it spatially varying over that boundary. I'm not going to do that for this exercise. For this exercise, I choose to have our harmonic water level. I'm going to edit then the conditions here. The frequency is 30, so that means exactly 12 hours. That's basically an S2 tide. An amplitude at the beginning of 1 meter and an amplitude at the end of 1 meter. Over the cross section it's constant. And there's no phase difference. And the upper row here describes basically the set-off, because there's no frequency, it's the constant value. So if you want to change your mean value of your boundary, then you can add an amplitude over here. If you want to raise it by 0.5, for example, you fill it in right here. I don't want that, I just keep my mean seawater level at 0. And then the second row reflects the tidal motion with a frequency of 30 degrees per hour, which is basically, and then it takes 12 hours to fulfill the 360 degrees required. So that is a 12-hour period. Again, I have to save this. C1, boundary save. Okay, I call it CO3. The harmonic flow conditions, I also call it CO3. And the time series. And the time series reflect the river flow. I call it CO3 as well. Then close. And then I say by save the MDF as CO3 as well. So now we have basically a river flow here coming in, a tidal motion at the other end. But now we want to add salinity. So we have fresh river flow, and we have salt tidal water. And the way to add that salinity difference, we have to add a process. So in the processes you can see the constituents, and we add salinity over there. If you add salinity, that means also your initial conditions will change. So there's salinity now prescribed here. So let's assume that it is everywhere 31 ppt. Salt water, that means that if you add river flow, that it will slowly wash out the salt water. And we have to revisit the boundaries, because at the upstream boundary we have to define whether it is salt or fresh water under transport conditions. We see that here at the lower end. And there's a salinity, it's uniform over the vertical profile, and by default it is 0 at the beginning, but we have to also add 0 at the end. And so this is totally fresh water flowing in. At the downstream side, we have to define transport conditions of the salinity, and we make that 31. So it's really salt water. Close. Now there's this other important aspect here, and that is called the Thatcher-Harleman time lags. And what does that mean? Well, you can imagine if you have a boundary that is tidally varying, tidally fluctuating. Sometimes water is flowing out the domain and sometimes it's flowing in the domain. If the water is flowing out of the domain, it can have any concentration of the salt below 31. So if it's totally fresh, it's 0. There's no salinity flowing out. But it can be also 20, 28. It can even be 31. Now, as soon as the tide turns from ebb flow outgoing to inflow ingoing, it means that the concentration will immediately change. So if you have an outflow condition of 0 salinity, then the moment water starts to flow in, it will have a salinity of 31 ppt. And that's not realistic, and it causes very large gradients in the salinity profile. What you would expect is that, of course, if water is flowing out of the domain, immediately if the water starts inflowing, that the salinity does not directly go to this 31, but it takes a while to go to the values defined at the boundary. And that's basically a time lag. And the Thatcher-Harleman time lag is then the time lag between the outflowing concentration and the boundary defined concentration. We typically set that at well, 60, maybe 1 hour. I put it at 1 hour here, but you can also put it at 2 hours. And so that is a relaxation time going from the outgoing concentration towards the boundary defined concentration. We do that for the downstream boundary, but also we do that for the upstream boundary. It will make your model more stable, but what's more important, or also more realistic at the boundaries. Again, I do save all as, and all my files I'm going to call that CO3. Yes. It didn't save everything. There's still a star here. That means that the MDF file was not properly saved. So I'm saving my MDF file again as CO3. Save. I want to replace it. Yes. This is all nicely done as well. Save all. Well, the star is still here. That is strange. So let's see what the reason for that is. I'm going to start my model. Browse. Call it CO3. And it is running. In the meantime, I can start my quick plot to analyze the model results. So I'm not saying that this is a very realistic model, because the model length is about 12 to 13 kilometers, and with a flat bottom. So that means there's a flat bathymetry. In realistic estuaries, the basin would be, well, it will have channels and shoals, and it will be, I mean, the bathymetry will not be fully horizontal, of course, and maybe after 10 kilometers there's a mountain, so the boundaries are maybe not very realistic. But it is also good to show what a model like this can reproduce, so that you can apply it in more realistic models. I'm now opening the file during the run by opening the trim file, and I'm going to look first at the water level. It's always good to check if the basic parameters like water levels and velocities show realistic results. And that is indeed true. You see that there is a water level slope from 0.3 at the inflow to minus 0.4 near the sea. And we can also now select a cross section like this, and then take a look at the water level over there. And so it means it's almost low water, and that's what we see over here. And I'm going to reopen the file to have the latest results. And so this looks a little bit different. I'm going to make a movie out of this to see what's happening. And in order to have a constant y-axis value, I'm going to zoom in a little bit. And if I zoom in, that means that my y-axis is kept constant. And if I don't do that, I have my y-axis values will change over time. I don't want that for this movie. So we just drag the zoom, yeah, and start from the beginning, and then I press my movie button here, and this is what the model shows. And you see that the water level goes up and down, forced by what is happening at the downstream boundary by the tide, and you see a tremendous backwater effect, but also the upstream boundary water level goes up and down. Now, if we want to, we can also now look at the velocities, and I'm not going to look at the depth average velocity because it's a 3D model. But I'm looking at the velocity itself, and we can do that in vectors, but yeah, let's do that. Use colored vectors to represent the magnitude and the color. And, want to have the latest results again, and make a movie of this. Zoom in again. Of course, the water depth is at 5 meters, so it will not be much more than 5 meters, but I want to have the maximum vertical level being 1 meter. I want to have that included as well. Yes, there it is. So pressing the movie button again. So what are we seeing here? We see that there is a constant flow velocity downstream. And because there's so much water supply by the river, I don't see water going back and forth at the seaward boundary. Because the river flow just always overrules the tidal motion. So this is basically a backwater effect. Well, let's prevent that a little bit, because I don't like that. And let's stop the run, exit, and let's make the inflow a little bit smaller. We go to boundaries in the MDF file, edit flow conditions, and not 0.8 but make it 0.3 everywhere. And save all, and I'm starting again. I'm reopening the file. Of course, we have to wait a little bit. So a quick view. There's some initial disturbance of the flow. Wants to find a kind of equilibrium. But what I already see in this plot is that over the vertical there's quite a gradient. So at the upper part there is high velocities, and at the lower part there's very low velocities, and that's logical, because we now have salinity gradients, and the fresh water will be probably on top. So the fresh river water will be on top, and it's flowing out over the model domain. Whereas at the lower portions at the seaward boundary, the salt water also wants to intrude. So you get this density driven currents. And hopefully we are seeing later on in the next update that we see the tidally varying flow, and we also see these conditions where maybe river flow may flow out at the top, but seawater will flow in at the bed or near the bed. Let's see if that's happening as well. I'm going to set the velocity magnitude color bar, not to automatic but manual. I'll put it to manual. So I'm reopening the model again. Going to set the the velocity is now, the color bar is also fixed. Quick view, make it large, and let's see what's happening. So this is the startup of the model. You see that vertical velocities are allowed here. See that there's sometimes reasonable, fairly large vertical motion of the water. And now it seems to be more stable. And indeed there are some occasions where you see indeed this inflow of salt water. Let's see. Yeah, here you see the outgoing flow, and at the top and at the near the bed you see incoming flow. And what you also see is all the kind of these vertical velocities that really mix the water because of turbulent friction, and so that is all included in the model. Here you also see that there's very large outgoing flow, fresh water probably, and incoming flow near the bed. So let's have a closer look at the salinity. The salinity is now also an output parameter. You find that here. And the color limits, I put it now to 31, because that is my highest salinity that I would expect. And let's have a look at that. This is indeed very interesting. So the blue part is the fresh water, and the red part is the saline intrusion, basically. And let's have a movie on this as well. By the way, if you want to save the movie, you can, under no output, you can go to AVI file, and that generates an AVI file that you can use for presentations and so on. So that's useful to know. I'm not doing that now. I have no output, and I just continue. So in the beginning, everything is 31. You see that the I'm going to have to fix the y-axis values, and I do that by zooming into the model domain, because zooming then makes the axis fixed. Right. See indeed the tidal motion going up and down. You see the fresh water on top, salt water in the middle, near the bed, and you see the intrusion of salt, which is sometimes a lot, and at the end of the ebb it is limited, and then the flood comes, and at the end of the flood there is more salt intrusion. And you see indeed mixing of the salt water. Especially the upper layer may be totally fresh, but underneath there are already, due to mixing processes, vertical motion of the water, and there is already a little bit salt present. And apparently we have a condition here where the salt water does not intrude more than 10 kilometers over here. But if I would increase the flow velocity at the riverside, that means it would wash out all the salt. And at the same time, if I would increase the tidal prism, or the tidal amplitude, that would put more pressure on the salt intrusion, with more salt intrusion length as a consequence. Now we can also take a look at it from another perspective. We just made a cross section along the model itself, but we can also use the entire domain and have, for example, the upper layer. We have that here, that is totally fresh, and we have the lowest layer, and here you can see this is at the same time. The upper layer is totally fresh, and the lower layer, you see, is for a large part it's very salty. Other interesting parameters may be the turbulent kinetic energy. That's the turbulent energy. That is here. I'm not sure what put it at automatic. Automatic. And you can see where most turbulence is. Let's see. The limit is manual. Let's see what that is doing. Especially this turbulent kinetic energy is very important for the mixing of the water, and this is the vertical mixing. So I'm looking at the vertical mixing generated by the boundary layer of the bed, and I have to set the ranges a little bit differently, and let's see what is coming out here. If I set the range too large, so I will adjust that a little bit. Well, maybe the range is also not very interesting here. You see a little bit turbulence generated at the landward boundary, and also here at the seaward boundary to a lesser extent. Because probably the flow velocities and the gradients in flow velocities are largest near the landward boundary. Well said, this is a very academic exercise. It's not very realistic, probably, because in reality there will be much more channels and shoal that also create a lot of turbulence, also in the horizontal and in the vertical. But this is just a kind of proof of concept that the model can deal with 3D salinity intrusion effects. So thank you for your attention, and looking forward to seeing you at the next exercise.